Good afternoon. Last official lecture. Aren't you glad? Don't applaud. Okay. So next week is just review, and on Friday is a lecture about Berkeley and the actinides, where I would love to see you all. I also like to see you in review. I said 9 o'clock and 1 o'clock. 1 o'clock will be even webcast, but no more eye clickers. Today, the last use of eye clickers, okay? What you hear here is subject of our, can you hear that? Somebody is calling from Mars. Every time you hear this, there's a radioactive decay hitting this little counter. So we will talk about radioactivity today, all right? And this is natural radioactivity that you hear. So we are bombarded by radioactivity. See that little tiny little counter? We will show it to you later. And this is about this big, and this many decays happen on the surface of this coming through the air, all right? So let's talk about this a little bit more. Oh, I want to say one thing. Last time, one of your colleagues said to me, you know, this redox thing, redox equilibria, is just like acid-base. Of course, one could make this analogy, but be very careful. Acid-base reactions are not redox reactions. There is no change in oxidation state. Remember that, okay? All right, good. So, radiation, we know particles and waves, and radiation can be both. Can be particles and can be waves. And if we have non-ionizing radiation, this is infrared, microwave, radio, NMR, MRI, they're non-ionizing, so they're not that harmful. It starts with visible, with UV actually, with X-rays, and with gamma rays. Gamma rays are essentially photons. X-rays are photons of a higher energy. Gamma rays have a higher energy. This is 10 to the minus 16 hertz here, and X-rays have about 10 to the minus 10. So gamma rays are actually not particles. Insofar, they are particles because they act as photons, okay? But they are actually waves. They are not corpuscular radiation, all right? What is corpuscular radiation? We'll talk about this in a second. So this is ionizing radiation. That means it can ionize chemical substances, can ionize your cell, can damage your cells, and of course you have a very good cell repair mechanism in your body. And some people says even you need to be a little stimulated by ionizing radiation in order to get the repair mechanism constantly going. So we need to have some repair mechanism because obviously we are subjected to radiation constantly. And this is not coming from anything outside. That comes from space and from the soil here and from our environment. And this is not the environment we created, it's the natural environment. So radiation is omnipresent, okay? You're going to be zapped at the moment many times, every time you do. You also have radiation in your body. When you eat, a banana has radiation in there. Please don't stop eating bananas. There's potassium in there. It's very good for you, potassium, if you do lots of sports, and good for your heart. But potassium has one radioactive nuclide in there, which is potassium 40. It has a very small amount, but it's radioactive. And so you are radioactive, essentially. And never mind, I can talk about all kinds of things. So this is waves. So gammas are obviously waves or photons. You could look at this as photons. And then there's particle radiation. So you have the nucleus is made out of protons and neutrons. Okay, we know that. Protons and neutrons. Not every nucleus is made out of protons and neutrons. Which is the nucleus that's not made out of protons and neutrons? Combination of them. Which is it? Hydrogen. It's only made out of protons. But if I have deuterium, you have a proton and a neutron. Then you have heavy hydrogen. And you have very heavy hydrogen. You have two neutrons and one proton. This is called tritium, okay? Especially in molecular and cell biology, you will use this in the biochemistry. So the radiation comes out of the nucleus, okay? Comes out of the nucleus, and you can have several different things coming out of the nucleus. One could be and an alpha radiation. And radiation was discovered the first time around 1898 in the century before last century. And this was discovered by Marie and Pierre Curie and Henri Becquerel. And they won the Nobel Prize for this in 1903, the Nobel Prize for Physics. All right, and then there was this guy Rutherford. He came from New Zealand, and he was in Cambridge and all kinds of different universities. And he worked a lot with radiation and tried to find out what is that radiation. They didn't know much about the nucleus at all at the time. They barely knew about the electrons. Actually, they didn't know much about the electrons at the time. And so he says, okay, there come these particles out there, and I call it Greek alphabet, I call it alpha radiation. That's all. That's the first one, okay? Alpha radiation. And alpha radiation are nothing but helium nuclei. Helium nuclei, okay? That means helium is element number 2 and has 2 protons and 2 neutrons, and they are, the nuclei are positively charged because they don't have electrons. And so the nucleus spits out this helium particle because it's unstable. And alpha decay only happens with elements that are above bismuth, so very heavy elements above element number 83. Or 83 does it already, but 83 somewhere above. So there you have alpha decay. And then there's other decay. So this you can stop by paper, and I will demonstrate this to you. Then you have beta minus decay. There's an electron coming out of the nucleus. The nucleus spits out an electron to get more stable. And that electron has, of course, a negative charge. And this is called beta radiation. Alpha, beta. That's the second one they identified. They say that's beta radiation. And this is beta minus radiation. Because the other possibility that the nucleus can spit out a beta plus particle. What would that be? A positive electron would be a positron. Instead of having a charge of -1, it has a charge of +1. Okay? And we call this a beta plus particle. And this can be stopped by skin and clothing. So let me introduce you to some of the radiations that I have mentioned here. And let me give you this screen here first. Okay, now I can take this off here. So I have what you hear here is a Geiger counter. And you will see this very soon in the picture above you. A Geiger counter. Is that the picture above? There it is. Yeah, also I have a different one here. Okay, good. So I have to look up there. Ah, thank you. Thank you. Okay, good. I would like to have this on the monitor too, but that's a different story. Excellent, excellent. Thank you. So I have here a piece of, what is it, ceramic. See that? That's nice and orange. That used to be called Fiesta ware. It was very popular in the 50s and the 60s here, had this beautiful color, pop art, okay? And so people, they had plates and cups and a whole dinner service or a breakfast service made out of this stuff. And they also had tiles in their bathroom. And this is radioactive. It's uranium oxide. It's radioactive, so it's not going to hurt me, but when you eat on it, there will be some of the radioactivity activity slowly getting into your body, which is not very good. If you have it tiled in the bathroom, people at the old times, they weren't that often in the bathroom. It was not like a spa, okay? So people, they went to the bathroom and came back out, and that was it. Took a shower once a week, whether they needed it or not, and that was it, okay? And so let me put this here on this Geiger counter. This is a Geiger. You see the scale here? This is the Geiger counter. And now we need to listen to it. Can you hear it? No? You can't hear it? And you can see it. You can see how it's pegging here? Let me do it. Okay. So this is obviously, the Geiger counter is sensitive to beta and gamma radiation. Okay? Beta radiation, you can take a piece of plexiglass here, and I put it in between, and most of it is gone. See that? It's absorbed by plexiglass, beta radiation. So you see in these labs where they use tritium and they use other beta emitters, they have these plexiglass shielding around them that they do not expose themselves to the radiation. See the difference here? And so if you have gamma, if I put a piece of lead over it too, a piece of lead under it, it should make a difference. I doubt it that it makes a big difference. Not much. Okay, the lead is not thick enough. So the gamma, so we have a mixed source. We have beta radiation and we have gamma radiation, and there's also alpha radiation, but this doesn't detect alpha radiation. So now I'm going to take a pure beta emitter. You see that this is strontium-90, which has a half-life of 20 years. That means in 200 years, it's totally gone. There's 1 in 1,000 left. And so, see the difference? So we have background now. Can you hear this enough, the clicking? Yes? Okay, good. All right, so that's a pure beta emitter. And now we're going to do a gamma emitter. This is cesium, is it gamma? Let's see, cesium-137. Cesium-137. Not so much, huh? So now I'm going to put some lead on these. That makes a difference. The lead's not thick enough. Let me put some more lead in there. So if the gamma radiation, which is our waves, they penetrate very easily, and so you need, so I'm holding this here now, it's kind of juggling, see that? All right, now I'm going to pull this away here. It changed. Now I'm going to pull this away, and it changed too, okay? So with this I shield the betas, and with the lead I shield the gammas. And you need a lot of lead to shield gammas because they are not very interacting very much with matter. Okay? Now we want to use another counter. Oh, I want to show you this glass here. This is a nice glass for liqueur for my grandmother. And this has a nice green uranium color here. This is green, so it's radioactive, but I'm not going to die from it. And if you don't drink so much, it will be not a big difference. Can you hear it? Let's go back. You hear it? Okay. The radioactive glass, the radioactive bathroom towels and Fiestaware, and the radioactive glass. So now I'm going to use another counter, and this counter is a alpha counter. It only counts alpha radiation. Can't count any other radiation. Let's see, how can we do that? Can you hold it? But they need to see it in the front. Okay, so there's my probe. All right, so I'm holding now, this is alpha radiation. Okay, and I take a piece of paper, and I'm putting it in between. It's very high energy radiation. It's 4.8 MeV, mega electron volt, has very short reach. That's what you could use for alpha cancer therapy. If you get this, it will damage the cells, but it will not damage my skin if I don't have it always there. But if you incorporate it, then it sits in your body organs, and then it will damage the cells right next to it. Okay, one more time. So you've seen there are three different kinds of corpuscular radiation. That means particle radiation. And the other radiation is the radiation that is a emission of gammas. Think of radiation as birth, okay? Compare it with a mother who gets a child. So the mother gives the child comes into the world, and so what you have, so it spits out, let's say that's the helium particle, it's a big particle, would be the child. So if you ever watched a video of a mother giving birth, that's pretty frightening for somebody who is not female. Actually, it's frightening for people also who are female. So they're in an extremely excited state, these people, okay? And then they are still, but they are very happy when the child is born, but they are still in a very excited state, okay? So this is what the nucleus is. It spits out these particles, and then it's in this excited state, okay? Now it's in this excited state. How do you think it gets back to normal? I mean, the mother takes a couple of weeks to get back to normal, and there will be the weight loss and all this stuff and so on, okay? And then the mother is back in the ground state, okay? It will take a long time, actually, all right? But that nucleus is up here. So how do you think it's an excited state? Did you hear about excited states with electrons? Yeah. So how did these electrons go from the excited state back into the ground state? They emit photons. They emit light. That's exactly what the nucleus does, just of a higher energy. That light is higher energy is gamma radiation, okay? And so it emits gamma radiation. Either it goes directly in the ground state, or it goes through some different levels. We've seen the levels. We had this with electrons. But this is nuclear radiation, okay? That comes from the nucleus being in the excited state, going to the ground state. So what you can learn is that there is always gamma radiation involved with any other of particle radiation, okay? So if you have a beta minus decay or beta plus decay, there's always, or the alpha decay, there's always that excited state of the nucleus, how it is left behind. So that's the new nucleus, because the nucleus changed, and we talk about this, how it is left behind. It will go down to the ground state as radiation, as gamma radiation. So I think we can shut this off, that you don't get paranoid here about this. It's the wrong meter. Okay, good. All right, so let's talk about this exposure to radiation. That's what you heard at the beginning, this background radiation. We have a radiation background on the Earth here. So we are constantly exposed to radiation, all right? You want it or not, it has nothing to do with us. It has to do with the universe. It has to do with the Earth, okay? So there's cosmic rays. Out of the cosmos coming all kinds of particles. There's protons, very high energy protons is about 90%, and helium is about 7%, high energy helium particles. And lithium, beryllium, boron, carbon, nitrogen, and oxygen make about 3% of the total here. And they hit the Earth's atmospheres, and then they produce neutrons and protons and photons and charged particles that are reaching us, okay? And this is what you hear. That's the background radiation. That's called the cosmic radiation. And if you are higher up, if you fly an airplane, you are closer to it. And with this, your dose is higher. So if you fly a lot in airplanes, you get a higher dose. Or you live at 7,000 feet or 10,000 feet, you get more radiation than if you live at sea level. Okay? And this is one of the problems with Mars exploration, where people want to go to Mars, because the radiation field on Mars and on the way to Mars is so incredible that if you have any human being want to go to Mars, you have to shield them tremendously from this radiation. So you have to use very heavy shielding, lead essentially, and that makes that spacecraft very, very heavy. And so it's very difficult to get it off the ground. That's one of the biggest problems, and it's not really solved, okay, of space flight further than the moon. Even in the moon, the people had huge pits in their helmet from the radiation, actually. Okay, when they hit the radiation, hit their helmets, if they magnified this, there was huge pits from the tracks of the radiation in their helmets. So this is what comes from the cosmos, but we also have terrestrial sources. We have naturally decaying radioactive elements. We have thorium and uranium is omnipresent. Uranium, if you could take the uranium out of the seawater, if you could concentrate this, you would have uranium forever. Forever, you know. You also have gold in the seawater. It has nothing to do with radioactivity, but it's too expensive to extract the gold out of the seawater compared to the prices we have now. But so there is natural radioactivity. It's called from terrestrial sources. That means Earth-bound sources. There's lots of geologic material, rocks, soil, natural decay series. They have these natural decay series of uranium and thorium. And in food, you have, I told you about potassium. In your banana, there's potassium 40. If you eat kiwis, you even have more potassium 40. Okay, with this you have more potassium. So the unit kiwi will be better for your heart than the unit banana. Okay, so eat more kiwis. No, I should get some checks from these guys. So what is exposure? Exposure is given in Röntgen equivalent man. That also can be for women, but this is milligram, 1,000th of it. So this is what you can't avoid, all right? And it's actually something which stimulates your repair mechanism of the DNA. Yeah? So there is radon in houses. If you look, the uranium, the natural uranium, decays to radium-226, 222, and this is a gas, okay? And the gas then goes back to the next decay product, which is 222 radon. Its radium is 86, and so let's see, 222, then 224. It's polonium, actually, okay? Polonium, and the polonium itself is then a particle again. It's not gas anymore. So if you breathe radon, you automatically breathe radioactivity, which deposits in your lungs. So there's nothing you can do about it. But if you smoke, you get a lot of radon. Actually, you get 1,300 carcinogenic compounds in each cigarette, every smoke. Smoking is very good for your figure. It makes you very slim. So slim that you even get dye from it, okay? So you're very thin at the end, okay? But I used to smoke 40 cigarettes until I was 34, so I have no way to say anything, all right? So somebody has, but you still have some time to go till you're 34. So, or maybe you don't start, that's the best. So there's 55% of your natural exposure comes from radon, and this is also, it's not so much here. Our houses, they are very leaky, okay? Even if we put all this insulation in there, they're made out of wood, and so they leak very nicely. So the radon comes from the soil under the house and seeps into the house, and then if the house is very well insulated, like in Scandinavian countries, or in countries, in parts of our country where it's very cold, we're starting to insulate better, so then it can't leave the house. And so you're breathing this in, and there's an indoor radon problem. It's really a serious problem. So what you need to do, open the window a couple of times a day and let the radon out. Or you have your basement is even better. You have my basement insulated from the main house and have it constantly put air, circulate air through there. That way you can avoid that. So your medical x-rays is about 15%. So you get 55 milligrams if you are healthy. If you're not healthy, you get a lot. And so, of course, there is, I'm not accusing anybody in particular, but there are a lot of doctors who have this expensive machine, and the more people get in front of that radiation machine, get some diagnosed for it, and even if there's nothing wrong with them, that will be ka-ching, 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 will be money in the register of the doctor, in the cash register of the doctor. I'm not accusing any doctors that they're doing this. Of course, they won't do that. But I, for example, used to go to a dentist, and they wanted to do every several years, they wanted to do a full x-ray of my head. I said, what's that for? So we do this routinely. I said, is there anything wrong with my teeth? No. So why don't you do the little ones? And they are even digital, and so they're lowering constantly the radiation dose that you get. And I say, you see anything wrong with this? I said, no, but we need to see the whole head. I said, I don't think you need to see the whole head because there's nothing wrong with my teeth. So because I know about radiation, I keep it to an absolute minimum because I don't fall for this kind of stuff, you know. But the general population, of course, they said, oh yeah, the doctor says that I need a head x-ray, let's do that head x-ray, okay? And so you need to be an educated citizen, and if you are only educated if you have education, all right? So cosmic radiation I talked about is about 25 milligrams, it's about 10%, and they are very terrestrial radiation. For example, out of these walls are concrete, here, there's radiation coming out, okay? Radiation, uranium radiation comes out of this. We count this here, actually, with our counter. And then you have from food, you get it out another 25 milligrams. This is what the uranium grows, or the food, much of the food grows in soil, and the soil, the plants enrich it, and then you eat it with the plants or with the animals that you eat that ate plants. This is how the rest of the radiation gets into you. So, but there's nothing wrong with this, okay? Not that you start living, okay? Said, oh, so much radiation. No, actually, there's not much radiation, and it's a natural thing, all right? So, and from man-made sources or people-made sources, you get about 3%. That's 9 milligrams. There is, for example, this exit I doubted that this has tritium in there, but in airplanes, and so the exit signs that have to be really reliable, they are filled with tritium. They glow even then in the dark, okay? And your smoke detectors, they have americium-241 in there, and they constantly ionizing that little bit of air that is in the smoke detector, and when there comes smoke, and they measure the current. And when the smoke comes in, then suddenly the current changes because there are more particles, and immediately it goes off, okay? And every smoke detector in the world has that. And this is what the people who invented or who made the first time americium-241, they never thought that they would be able to use that. So if somebody asked me about, you make element 114, what's that good for? I said, for nothing, for our understanding of science, okay? But we didn't know that many elements that were discovered at one point that were made were good for something or not good for something. But plutonium is used for peaceful and non-peaceful things, for example. And others, this is, for example, from nuclear fallout. There was above-ground testing in the world and in the United States, and China did the last above-ground test, and you get less than 1%. And if you're right next to the door of a nuclear power plant, you get less than 1% exposure compared to this here, okay? So it's so why is there radioactivity? Why is there radioactivity? So you have the neutron and the proton and the nucleus. And if you look at, for example, at helium, just helium as an element, helium has 2 neutrons and 2 protons. So this is a neutron to proton ratio of 1 to 1, okay? Now, if we go up there, so the lighter ones, they have a neutron to proton ratio of 1 to 1. If you go up then, and this is stable then, if there's a certain ratio, if the neutrons and protons have a certain ratio, then they are stable. The element is stable. So if you go up here, iron, for example, has a ratio of 1.2 to 1. Iron 56 would that be. So this is stable. Now the next one would be cadmium, just as an example, has 1.3 to 1. This is stable. Mercury has a ratio of 1.5 to 1, and it is stable. So the stability, that's the line of stability or the zone of stability. If they are around here, the ratio between 1 for the lighter ones and the heavier ones, 1 to 1.5, neutron to proton ratio, they are stable, okay? And if you have a different ratio, you have radioactivity. It's unstable. It wants to reach that ratio that it makes it stable again. So it will do it by either spitting out whole particles, okay, that's a possibility, but that doesn't make it really stable because whole particles are alpha particles. Everything above 83, including 83, is bismuth. So bismuth is element number 83. Everything above is actually alpha radioactive, okay? That decays alpha. All these lighter ones, they don't have alpha decay. So everything above is radioactive above bismuth. And so what you have, the actinides, for example, but they all do alpha decay. Now, so you see the stable light nuclei have a ratio of 1 to 1, neutron to proton, and the stable heavy ones have 1.5 to 1. So this would be a 1 to 1 line, which is irrelevant, okay? You want this ratio here being on the line of stability. So if you are here, if you, for example, sit with a ratio here that has, what does this have? It has not enough protons, okay? So that would be not enough protons. You would have to get over here somehow. So a neutron would convert itself to a proton and what else? A beta plus particle, okay? I will go through that. If you are here, that would be that's the beta minor region. So what would that be? You have too many neutrons, okay? Yeah, you have too many neutrons, of course. The neutrons would go into a proton and a beta minus, okay? So now there are also nuclear magic numbers, just like electrons have stable orbital configurations, okay? So there was, when you had neon and argon and krypton, when n equals 1, n equals 2, n equals 3, when this is filled, the orbital is filled, then you have stability. And the same thing happens, actually these are shells. You have certain neutron and proton shells, and there you can talk about shells. These are not orbitals. They are shells in the nucleus. And when there are certain numbers of neutrons and protons, then they are more stable, okay? They have stability. And when they have both shells have one of these magic numbers, you don't need to know those, have these magic numbers, they are double stable, okay? They're even more stable. So when the neutron shell is a magic number and the proton shell is a magic number, they are very stable, okay? So you don't need to know, you need to have heard about magic numbers, but you will forget that soon. So now these neutrons and protons are bound in the nucleus. Just like the electrons are bound to the nucleus, and we call this binding energy, and we call this also binding energy, and we call this binding energy per nucleon. And so when you make them bigger and bigger, these nuclei, so you have to have more neutrons in there in order to accommodate the positive charges, all right? Otherwise it would not hold together. So if you look, for example, at element at the beginning, hydrogen, for example, has one proton and no neutrons. It has a binding energy inside the nucleus of about 1 MeV, mega electron volt. That's an energy unit, mega electron volt per nucleon, okay? So if you have a mole of those things, you have to multiply it by 6.02 times 10 to the 23rd, all right? So as you see, if you increase the proton numbers, the binding energies get bigger. See, get much bigger and bigger. So they are stronger and stronger bound. So when they form, they release all this energy. Binding will release energy. Well, they formed, they release all this energy, and this is what happens in the sun. Real solar energy, where you have fusion. And what you do, you fuse hydrogen and heavy hydrogen to helium. There are many such reactions going on the surface and in the sun. But you have fusion, and if you look at this hydrogen and heavy hydrogen makes then helium, you see you release all this binding energy per nucleon, all right? And with this, tremendous amount of energy you can release, much more than you ever get from chemical reactions, all right? And this is why nuclear is a very promising, nuclear fusion is very promising. And when you talk about, so the highest one binding energy is iron 56, that's why I mentioned this. It has about 8.5 MeV, and you will learn what this means, per nucleon. But then if you go higher in C, increase in atomic number, it goes down again. And now here is uranium, uranium-235. It can be split. It splits in two nuclei. When you put some neutrons in there, it splits in two nuclei, one lighter one, a little bit lighter, one heavier one. And so one would I call krypton, that's the lighter one, and then I call a heavier one would be barium. And when they form, you see their binding energy per nucleon is higher, you see that, than uranium. And so you release that energy when they reform here. When this explosion happens and they reform, they release that energy, okay? And so what they also release, each of them releases about 2.5 neutrons per fission. And so these neutrons can fit into new uranium and fission more and more. And with this, you get actually a chain reaction, and you have to make sure that the chain reaction doesn't get out of hand. But this is not part of that lecture here. So you could use that, for example, there's combination of lighter ones and heavier ones, okay? This is one of those combinations. So this is how nuclear energy works, and I would have loved to talk to you about this, but we only have one lecture on this, and I try to give you as much as I can. So let's talk about these decays now systematically. Alpha decay is uranium. These must be heavy, higher, or at bismuth, element number 83, you can have alpha decay. So it spits out that helium particle, helium-2+, and so it reduces this by 4. This is then 234, and the atomic number is reduced by 2. And you know that element number 90, if this is 92 here, element number 90 is here on the periodic table. You have thorium then, so if this makes an alpha decay, you get thorium-234, all right? So this is the systematics for an alpha decay. A beta decay, and this is what I tried to explain to you before, A beta decay is a neutron goes as a nuclear neutron, so you have too many neutrons, okay? You have too many neutrons. So that means a neutron and not enough protons. So the neutron says, okay, I'm going to become a proton. But I become a proton, and I have an electron with this, because the proton is positively charged. So in order to balance the charge, I need to make an electron, a nuclear electron. It's not in the electronic orbitals. It's a nuclear electron, and that we call a beta minus, because it has the charge of beta minus. So what happens? 53, this goes away, so this is 54, so this comes out. One of them, so the proton and the neutron goes into a proton, 54 makes 54, okay? And the nuclear number doesn't change. So you go one up in atomic number, and then this is an antineutrino. Only the physicists would be interested what it is. This is actually it turns out to be a particle. People are hunting for this. This was believed to be massless, and this is for the conservation of momentum. And now in recent experiments, very huge experiments, people find out, or my colleagues find out, that this does have a tiny, tiny, tiny little bit of mass, okay? And so this is the neutrino, that's for the conservation. Actually, it's the antineutrino. I'd love to talk to you about matter and antimatter, but it's not subject to that class, and they cut me by 1 week, all right? So in the beta plus decay, so this happens when you have protons, and too many protons. So the proton says, okay, I better become a neutron. And since this was positive, I got to have a charge balance. So a neutron plus a positron. That's an electron with a positive charge. It's the antimatter, essentially, of the electron, okay? It's the positron. And with this, you see, this comes out. The proton goes in a neutron. So that 11 goes to 10, because I lost one proton. And I spit this out. This is the positron, or the beta plus particle. And with this, I go to neon 22. That number doesn't change. And then neutrino, okay? That's the same thing, just with a different spin. But there's another form. Actually, the electronic orbitals are involved. So the nucleus sits there, and it says, I have too many protons. I need some electron. And it captures an electron. And with this, it makes a neutron, okay? So the electron has a -1 here, and so it becomes then gold. So this is electron capture. It actually sucks in, like this, an electron out of the innermost orbital closest to the nucleus, okay? What will happen, of course, you will also have the emission of X-rays, because you just now are missing an electron in the S orbital, and so you have these other orbitals filled with electrons. One will fall right into that and emit gamma radiation, or X-rays, photons, okay? Never mind, all right? But we live, unfortunately, in a very negative world. Positrons are very unstable. So if you emit a positron, the world is full of negativity, unfortunately, of negative electrons, okay? So a positron immediately finds a negatron or an electron, okay? And what it does, this is obviously mass, okay? And it suddenly is converted into energy. They annihilate each other, and they form two gamma rays. So who was that guy who said that this would be possible? Einstein. E equals m times c squared. The energy is the mass times the velocity of light squared. And so we will talk about this a little bit. So this is annihilation. So if an electron is emitted at beta minus decay, then there are no beta pluses flying around, okay? So that will be stable. But if you have a beta plus, this is positron emission. You ever heard of positron emission tomography? PET? That's exactly how it works. They attach one of those beta emitters to a molecule that is specific for something they want to look in your brain. Usually they use glucose or something, and then they inject it in you, then it goes into your brain, and with this they can image your brain, all right? They can say, when you start thinking, this lights up, and when you start doing this, this lights up. And this comes because you have these two gamma rays. You see that what happens here? Boom, they hit each other, annihilate each other, and in 180 degrees, they emit these one gamma ray here and one gamma ray there. So if this would be in the head, okay, in the brain, so you could have a ring of detectors here, around there, and the gamma ray goes here, the gamma ray goes there. This goes there, this goes there. So we detect those, and of course, depending on the location, this would be in the middle, but if it's not in the middle, you can visualize the brain. You calculate the time it took from the brain to the detector to register, and then you process this mathematically, and with this you get these beautiful images of the brain of positron emission decay. And unfortunately, I can't talk much more about that either. So this is the principle of this. The change in energy is 2 times h times nu, is the change in mass times the speed of light squared. So the change in mass, let's do that calculation for just one such decay. How much energy is there? Now, the change in mass, the mass of an electron is 5.48 or 49 times 10 to the minus 4 AMU. You know, AMU was, we invented that, or we used that at the beginning atomic mass unit because it's such a small number. 1 AMU is 2 times 10 to the minus 24 grams. 2 times 10 to the minus 24 grams. And the speed of light squared is in energy is 931 MeV per AMU. So now what do? We're gonna, so it's m times c squared, we multiply this here. And then we put in here the AMUs. With this, we get 1.02 MeV per decay, per annihilation. 1.02 MeV. So how much is this in joules? 1 MeV is 1.6 times 10 to the minus 13 joules. And of course, you have to multiply this with the, for 1 mole. With this, you get 10 to 11 joules per mole. 10 to 11 joules is a tremendous amount. So do you have any idea how much a mole of bonds is about? How many joules? So we had 10 to the 5 joules per mole as a chemical bond, okay? A mole of chemical bonds, average chemical bonds, about 10 to the 5th. So there's a 5 orders, 6 orders, a millions more times energy you get out of this here than you get out of creating a chemical bond, okay? This is why nuclear is so powerful, okay? It provides a lot of energy. The nucleus has a lot more power in there than the electrons, okay? More binding power. And when they bind, they release energy. Remember? Binding is releasing energy. Breaking bonds, you need energy. Same is true for the nucleus. All right, now let's see if you understand. Let me give you that. Here, take out your TI 5 million. And we have the intensity of solar radiation is 10 to the 24 watt or 10 to the 36 MeV per second. What is the rate at which mass is lost from the sun? So every time you get radiation from the sun, you have that conversion, okay, of mass into energy, and that conversion is 10 to the 36 MeV per second. So how much is lost per second in weight of the sun? 1 billion grams, 1 million grams, or 10 grams per second? All right, why don't you give this a stab and think about it? Maybe you can solve it. So c squared is this here, okay? So what's the mass per second? The mass lost per second. And then you have to multiply it with your AMU, and then you get it grams per AMU. No, grams per second, because something is canceling. It's 1 billion grams, 1 million grams, or 10 grams per second on the sun. We don't see any change in the sun, don't we? Must be 10 grams. I doubt it, though. all the energy that comes to us. Very good. You can calculate. Excellent. All right, for those who didn't get it right away, I don't have enough time to let you discuss it, but I want to show it to you. It's a simple calculation. So we have 10 to the 36 MeV per second, okay? E, or delta E, is m times c squared. M is 10 to the 36 MeV per second, divided by c squared, okay? That's the energy. C squared is about 1,000 MeV, 931 MeV per AMU. I divide this, what do I get? I get 10 to the 33 AMU per second, and 1 AMU is 2 times 10 to the minus 24 grams per AMU. With this, the AMU cancels, then it has grams per second. It's 10 to the 9 grams per second, okay? And that is a billion grams, so that's a million kilograms, and a ton is 1,000 kilograms, so there's 1,000 tons per second, okay? 1,000 smaller cars per second, okay? Or not so small, actually. Per second, the sun loses, and you can't even see it because it's so big. All right, so 10 to the 9. Let me ask you another question, and this kind of stuff you need to know. Which nuclide is an alpha decay product of plutonium-239? You heard of plutonium. Plutonium-230, plutonium is element number 94, and 239 plutonium can be fissioned with neutrons, with fast neutrons. So what do you get? You get plutonium-235, neptunium-235, or uranium-235. I think this will be the last time you will be using your clicker in this class. Oh! Or the second to last time. This stuff you need to know. What does it spit out? What is it? 2 and 2 is 4. Instead of the level. What is it? See, I know that too. What was this? A was, what was, this was A, wasn't it? A, and B, this was B? Yeah, I remember. That's how we used to talk in school. Okay, so next week I will be there at 9 o'clock and at 1 o'clock. It will be just as usual. I will hold a review of the fourth unit on Monday and the overall review on Wednesday. And on Friday I will give a lecture of Berkeley and the actinides, and I would be very happy if some of you would show up. Okay? And so let's see if you have this right. Those of you who don't care to come anymore, I say goodbye, and I say thank you, and it was a pleasure of teaching you, okay? Bye, thank you. So let's see, there's the answer. Alpha, so 239 minus 4, 94, element 94 minus 2 is 92. That gives you uranium-235, and there you go, okay? Good luck to you.